In statistics, simple linear regression is the least squares estimator of a linear regression model with a single explanatory variable. In other words, simple linear regression fits a straight line through the set of endpoints in such a way that makes the sum of squared residuals of the model as small as possible. The adjective simple refers to the fact that this regression is one of the simplest in statistics. The slope of the fitted line is equal to the correlation between y and x corrected by the ratio of standard deviations of these variables. The intercept of the fitted line is such that it passes through the center of mass of the data points. Other regression methods besides the simple ordinary least squares also exist. In particular, when one wants to do regression by eye, people usually tend to draw a slightly steeper line, closer to the one produced by the total least squares method. This occurs because it is more natural for one's mind to consider the orthogonal distances from the observations to the regression line, rather than the vertical ones as OLS method does. Fitting the regression line, suppose there are n data points, xi, I equals 1. n. The function that describes x and y ISA, the goal is to find the equation of the straight line, which would provide a best fit for the data points. Here the best will be understood as in the least squares approach, a line that minimizes the sum of squared residuals of the linear regression model. In other words, I plus or minus and I squared solve the following minimization problem. By using either calculus, the geometry of inner product spaces, or simply expanding to get a quadratic in I plus or minus and I squared, it can be shown that the values of I plus or minus and I squared that minimize the objective function Q are, where Rxy is the sample correlation coefficient between x and y. Sx is the standard deviation of x, and Sy is correspondingly the standard deviation of y. A horizontal bar over a quantity indicates the sample average of that quantity. For example, substituting the above expressions for and into yields. This shows the role Rxy plays in the regression line of standardized data points. It is sometimes useful to calculate Rxy from the data independently using this equation. The coefficient of determination is equal to when the model is linear with a single independent variable. See sample correlation coefficient for additional details. Linear regression without the intercept term. Sometimes, people consider a simple linear regression model without the intercept term, y equals I squared x. In such a case, the OLS estimator for I squared simplifies to, and the sample correlation coefficient becomes. Numerical properties: the line goes through the center of mass point. The sum of the residuals is equal to 0, if the model includes a constant, the linear combination of the residuals, in which the coefficients are the x values, is equal to 0. Model-cased properties: description of the statistical properties of estimators from the simple linear regression estimates requires the use of a statistical model. The following is based on assuming the validity of a model under which the estimates are optimal. It is also possible to evaluate the properties under other assumptions, such as inhomogeneity, but this is discussed elsewhere. Unbiasedness: the estimators and are unbiased. This requires that we interpret the estimators as random variables, and so we have to assume that, for each value of x, the corresponding value of y is generated as a mean response I plus or minus plus I squared x plus an additional random variable I micron called the error term. This error term has to be equal to 0 on average, for each value of x. Under such interpretation, the least squares estimators and will themselves be random variables, and they will unbiasedly estimate the true values I plus or minus and I squared. Confidence intervals: the formulas given in the previous section allow one to calculate the point estimates of I plus or minus and I squared that is, the coefficients of the regression line for the given set of data. However, those formulas don't tell us how precise the estimates are, that is, how much the estimators and vary from sample to sample for the specified sample size. So-called confidence intervals were devised to give a plausible set of values the estimates might have if one repeated the experiment a very large number of times. The standard method of constructing confidence intervals for linear regression coefficients relies on the normality assumption, which is justified if either the errors in the regression are normally distributed, or the number of observations n is sufficiently large, in which case the estimator is approximately normally distributed. The latter case is justified by the central limit theorem. Normality assumption: under the first assumption above, that of the normality of the error terms, the estimator of the slope coefficient will itself be normally distributed with mean I² and variance where I2 florins is the variance of the error terms. At the same time, the sum of squared residuals Q is distributed proportionally to I2 with NA2 degrees of freedom, and independently from this allows us to construct a t-statistic where which has a student's t-distribution with NA2 degrees of freedom. Here c² is the standard error of the estimator. Using this t-statistic we can construct a confidence interval for I². At confidence level, where is the th quantile of the TNA2 distribution? For example, if I³ equals 0.05, then the confidence level is 95%. Similarly, the confidence interval for the intercept coefficient I plus or minus is given by at confidence level, where the confidence intervals for I plus or minus and I² give us the general idea where these regression coefficients are most likely to be. For example, in the Okun's law regression shown at the beginning of the article, the point estimates are the 95% confidence intervals for these estimates are. In order to represent this information graphically, in the form of the confidence bands around the regression line, one has to proceed carefully and account for the joint distribution of the estimators. It can be shown that at confidence level the confidence band has hyperbolic form given by the equation. Asymptotic assumption: the alternative second assumption states that when the number of points in the data set is large enough, the law of large numbers and the central limit theorem become applicable, and then the distribution of the estimators is approximately normal. Under this assumption, all formulas derived in the previous section remain valid, with the only exception that the quantile T₀ of students' t-distribution is replaced with the quantile Q of the standard normal distribution. Occasionally the fraction 1/N₀ is replaced with 1/N. When n is large, such change does not alter the results appreciably. Numerical example: this example concerns the data set from the ordinary least squares article. This dataset gives average weights for humans as a function of their height in the population of American women of age 30–39. Although the OLS article argues that it would be more appropriate to run a quadratic regression for this data, the simple linear regression model is applied here instead. There are n equals 15 points in this data set. Hand calculations would be started by finding the following 5 sums. These quantities would be used to calculate the estimates of the regression coefficients, and their standard errors. The 0.975 quantile of students' t-distribution with 13 degrees of freedom is t13 and equals a 2.1604, and thus the 95% confidence intervals for I plus or minus and I² are. The product moment correlation coefficient might also be calculated. This example also demonstrates that sophisticated calculations will not overcome the use of badly prepared data. The heights were originally given in inches, and have been converted to the nearest centimeter. Since the conversion factor is 1 inch to 2.54 cm, this is not a correct conversion. The original inches can be recovered by round, x/0.0254 and then reconverted to metric. If this is done, the results become. Thus a seemingly small variation in the data has a real effect. Derivation of simple regression estimators: we look for that minimizer sum of square errors, which is defined as: to find a minimum, take partial derivatives w at t, and by multiplying both sides by, we get. Before taking partial derivative w at t, substitute the previous result for. Now, take derivative w at t. And finally substitute to determine. See also, Deming regression, a simple linear regression with errors measured non-vertically, linear segmented regression, proofs involving ordinary least squares, a derivation of all formulas used in this article in general multidimensional case, references. External links: Wolfram Math World's explanation of least squares fitting, and how to calculate it.